Good morning, everyone. Am I clear? Loud? Is it audible? Okay. First of all, thank you for joining this session. The session will be primarily focusing on the different options available for deploying multicast over segment routing network. By way of introduction, I'm Nagendra. I'm one of the principal engineer with Cisco CX organization. I've been with Cisco for the past 14 years. And even working as a contract employee before that. So altogether, it's close to 20 years now that I've been working with Cisco. And I've played different roles. Started as a regression engineer and then dev as technical marketing, high-touch technical support, escalation. And right now, I'm part of the CX organization, working on different service innovation and strategies. I'm joined today by my good friend and co-presenter, Mankamana. I would let him introduce himself.
Good morning. I'm Mankamana Mishra. I'm from engineering team. And most of the time, I write code. I do internal designs. I have co-authored many drafts in IETF and all multicast, BGP, EVPN area. And I'm here to talk about some of the topics here. Thank you.
Thank you, Mankamana. So before jumping into the session, we would like to highlight the availability of this discussion room for this session. So it's not just the next 90 minutes that myself and Mankamana are available for any technical discussions. Even after this session, we can leverage this discussion room to continue or have any sort of technical clarifications specific to this topic. So feel free to join this discussion room in your WebEx app. That said, this would be the agenda for today's presentation. We'll start by sprucing up our knowledge on the basics of segment routing, because that plays an essential role to understand some of the multicast deployment options. And then we'll primarily looking into two different solution options. One is the controller-based approach, and the other one is a distributed approach. How many of you are new or relatively new to segment routing? Okay. How many of you have theoretical knowledge but have not played around with, got your hands dirty with segment routing? Okay. And how many of you are using in your production environment? Okay. So I think it's a kind of balance. So we'll spruce up our knowledge, the basics of segment routing in a pace that is not so very boring for who is actually familiar with segment routing. But at the same time, let's not leave the other friends behind. So the intent is by the end of the session, we'll have a better understanding about at least the basics of segment routing, which are essential to understand those multicast options. Fair enough? OK, so let's start with what is segment routing. Segment routing is a source routing paradigm-based architecture that basically encodes the path information as an ordered list of segment ID directly into the packet header, which could be used by the transit devices to execute the relevant course of action. So the segment ID here is one of the key components of segment routing architecture. Segment routing is nothing but a type of instruction with its own associated semantic, where the semantic could be simply forward the traffic over the shortest path to the destination, or to strictly forward it over a very specific path, or even to apply different types of services like deep packet inspection or firewall. Now, this capability that is introduced as part of segment routing, where you can define your own segment ID with its own associated semantic, helps us to innovate and come up with new solutions, or even to enhance the existing solutions. Now, is this the only benefit associated or that we can realize as part of segment routing? No, there are quite a few other benefits. Quickly speaking, control plane complexities. How many of you are using traffic engineering in your network? I'm sure you might be aware. I can see a lot of heads nodding. So with the RSVP-based traffic engineering tunnel, it's not just the head end and the tail end where we will be creating the state entries. Rather, all the transit devices that are part of the traffic engineering tunnel are required to maintain those state entries, which needs to be refreshed at certain cadence. So it introduces a lot of control plane challenges. If you look into a large network, it's pretty common to see thousands and thousands of tunnels for different use cases. Traffic protection, fully mesh connectivity, constraint-based connectivity. So with these control plane state entries, it always is a challenge. With segment routing, we are abstracting those state entries from the transit devices and have it in the packet header, thereby eliminating, or I would say significantly reduce those control plane complexities. Now, in the past decade, you probably would have heard the buzzword, software-defined networking. The initial concept or idea is to disaggregate the control plane from the underlying infrastructure or the devices and host it as a centralized entity, which will have a holistic view of the entire topology. Now, with this topology, we can do a lot of things. How does segment routing fits here? Segment routing not only helps us to simplify those control plane complexities, but also with this capability, the programming and automation capabilities, the ability to define new types of segment ID with its own associated semantics, helps us to realize the maximum benefits of software-defined networking. In simple words, segment routing fabric could be considered as the building block for software-defined networking. So we saw that the segment ID plays a key role. It's one of the important component of segment routing architecture. So we'll quickly discuss about a couple of very essential, fundamental segment IDs to understand how it works so that we can better understand the other segment IDs that are specific to multicast. We'll start with the prefix segment ID, IGP prefix segment ID. Any devices that are part of the segment routing domain will be assigned with a minimum of one IGP prefix segment ID. And this IGP prefix segment ID will be domain-wide unique. If you look at, theoretically, it's globally unique, but within the segment routing domain, it needs to be unique. It could be considered as similar to the loopback address that you configure in each of those devices within your domain. Now, the forwarding semantic associated to IGP prefix segment ID is to simply forward the traffic over the shortest path towards the destination device to which the prefix segment ID is assigned. Now let's take an example. Node 15 is assigned with a prefix segment ID of 16015. Any of those devices will compute the shortest path based on the IGP topology to reach node 15, and the particular egress interface will be used as the interface to forward any traffic that is received with the topmost segment ID as 16015. Here, if you look into node 11, there are two different ECMP paths to reach node 15. So both the egress interfaces will be used, and the traffic with any traffic with the topmost segment ID as 16015 will be load balanced between these two interfaces. The next one is IGP adjacency segment ID. Again, within the domain, each of the device will assign a locally unique IGP adjacency segment ID for each of those IGP adjacency. I repeat here, IGP adjacency, not the IGP neighbors. Now, this is one confusion that we have seen whenever we discuss about IGP adjacency. What is the difference? Node 2 have two different IGP adjacency to the same neighbor, which is node 5. So for each of those adjacency, a locally unique adjacency segment ID will be assigned by node 2. Now, the forwarding semantic associated to adjacency segment ID is to strictly forward it over the link to which the adjacency segment ID is assigned. So if the link is down, the default behavior is to simply drop the packet. There are quite a few other segment IDs that are defined over a period of time with its own associated semantic, but in the interest of time, we're not going to discuss everything. Rather, we just included here for your own reference. So feel free to look into it after the session. The next important component that we would like to discuss about is the path computation element, segment routing path computation element, or simply SRPCE. SRPCE is the SDN controller for segment routing. So we saw that SDN controller will allow us to have a holistic view of the entire topology. How do we achieve this? By using a new type of address family, BGP address family called BGP link state, which has the ability to extract the entire link state topology information from the underlying IGP topology, irrespective of the IGP protocol. It could be OSPF or even ISIS, and even it could be single domain or even islands of different IGP domains. By just having the BGP session with one or more of the device from each of those IGP topology, will be able to extract the entire information, end-to-end information. So this way, we'll be able to have a holistic view of the entire underlying IGP topology. Now, we have the ability to have this holistic view of the topology. By just feeding in the relevant business intent, we'll be able to compute, the path computation element of the server could be able to compute different types of paths that basically satisfies the relevant constraint for different applications. It's much, much granular. And by instantiating the relevant state entries, by using the combination of the segment IDs that we discussed, and the ability to encode this information directly into the packet header, we simplify the control plane, but still will be able to steer the traffic over any relevant path. SR PCE is available and can be hosted as a virtual XR device. So even using CML, you can host a virtual XR device and you can play around with this capability. It also supports, like I said, single domain or multi-domain, irrespective of the number of domains. By having the relevant BGP session, we'll be able to extract the entire information. And it also supports, the native SR algorithm. So not just the default, path, but even the flex algo, the multiplane, topology. Let's now see how the path encoding or path information is encoded in the SR header. Let's assume that there is an application which needs to steer the traffic from R1 to R8, but not through the best path, not through the shortest path. Rather, for one other reason, based on certain constraints, the traffic needs to be steered over segment 1, which is R1 to R4, R2 to R4, and from R4, the traffic needs to be forwarded to 5, and from R5, it needs to be forwarded to R8 through R7. To steer the traffic over this very specific path, all we need to do is inject 3 segments. The topmost segment would be the prefix segment ID of R4. So if you remember, we discussed that for prefix segment ID, it basically follows the shortest path. So from R1, it follows the shortest path towards R4, which is R1, R2, R4. And from R4, the second segment ID is the adjacency segment ID assigned by R4 for R5. So the traffic will be forwarded to R5. And R5 uses the third segment ID, which is the prefix segment ID, to reach R8. It follows the shortest path towards R8. By having this ability to inject different types of segments for different types of traffic, we'll be able to steer the traffic over those relevant paths. Segment ID, or the segment routing, can be applied both on the MPLS data plane and also on IPv6 data plane. In case of MPLS data plane, the segment ID is nothing but the labels. The SR header, or the ordered list of segment ID, is nothing but the stack of MPLS labels. On the other hand, in case of IPv6 data plane, the segment ID could be considered as the IPv6 address. Now, there are other fancy things like the microset, but let's not go there. For now, you can safely assume that the segment ID is nothing but the IPv6 address, and those ordered list of segment IDs will be carried as part of IPv6, a new type of IPv6 extension header called SRH. Okay, so far we discussed how we can use the segment routing architecture to encode those path information into the packet and steer the traffic. It works fine for unicast. But what about multicast? Is there anyone who's not using multicast in your network? Okay. So it's pretty common to see multicast in both enterprise and also in service provider network. If you look into an enterprise network, the application, there are different types of application which basically uses multicast for data replication or the data synchronization. It's not just the applications. There are even other services like media or video conferencing, or even video surveillance. So there are quite a few applications if you look into the enterprise network, where we may have a source which will be sending a traffic that one or more than one receivers will be interested to receive. It's not just the enterprise network. If you look into the service provider network, who's actually offering connectivity to different enterprise customers, in order to steer the multicast traffic from one branch site of an enterprise to another branch site, which is actually connected through a service provider network, the underlying service provider network is expected to support multicast, but in a multi-tenant aware manner. Because there might be multiple customers who will be using the same underlying service provider network, multicast VPN service. So irrespective of enterprise or irrespective of the service provider, basically irrespective of the segment, multicast plays a key role. And so by just deploying segment routing for unicast, we may not be able to realize the benefits that we are enjoying with unicast using segment routing for multicast traffic. If you look into the traditional multicast solutions, they are based on the traditional protocols like PIM, which builds the tree based on the shortest path. So whenever there is an interesting receiver, like IGMP, or any of those receivers basically express their interest to receive specific traffic, those edge devices will start building a tree towards the source and start receiving it. Now, it works fine, but there are quite a few, I wouldn't call it as a challenges, but probably limitations. If you look into the other benefits that we are enjoying with segment routing, like minimizing the control plane or bringing those SLA constraint awareness, not just the best path, rather steering the traffic over whatever path that basically satisfies my own requirement or the application's requirement, or even traffic protection. We do have some solutions over a period of time. There are some solutions that evolve, like for example, the ingress replication. Using the ingress replication, we can configure the edge device in a way that whenever we receive the multicast traffic, we can replicate the traffic and unicast to each of those remote edge devices by encapsulating with the MPLS label. So this way, we do have the ability to steer it over any specific path. But again, we are not actually solving the problem. Rather, we are moving the problem from one table to the other. The RSVP point-to-multipoint traffic engineering tunnel is another option. Again, you know that. We do have a lot of control plane complexities with the RSVP-based protocol for point-to-point tunnel. So you can imagine how it would be for point-to-multipoint tunnel. So what is the solution? Here in this session, we'll be discussing about two solutions. How we can bring those benefits that we are enjoying using segment routing for unicast, how can we bring them for multicast as well? So we'll be discussing about two solutions. The first one is the controller-based approach. We call it as segment routing point-to-multipoint policy. And the next one is a distributed approach, a multipoint LDP with segment routing extensions. So I'll be focusing on the first one, the controller-based approach, and our friend Mankamana will be discussing about the next one. Segment routing point-to-multipoint policy. So the SRP2MP policy is the SDN controller-based multipoint service or multipoint solution that basically builds a point-to-multipoint tree right from the root node to one or more leaf nodes through one or more intermittent replication nodes. Now, the root node could be considered as the ingress node, which basically receives the multicast traffic, perform the relevant encapsulation, and forward it inside the segment routing domain. The leaf node could be considered as the egress device, which receives the multicast traffic, the SR encapsulated traffic, decapsulate it, and send it outside the segment routing domain. The intermittent replication nodes could be considered as the branching nodes, branching points, which receives the SR encapsulated packet, replicate it, and send it to different downstream nodes. Now, with XR 7.3.1, there is another type of node which was introduced based on the demand, which is the bud node. So bud node is nothing but a node that basically performs multiple roles. The node can act as a leaf node and also a replication node. So there might be scenarios where you may have one of the node as the edge node, but also will be along the optimal path, so it needs to replicate and send it to other downstream nodes. So the node that acts as both leaf node and the replication node is what is referred as the bud node. Now, the point-to-multipoint policy can be static. The tree could be static, or it could be dynamic. There are different use cases where the root node and the set of leaf nodes are deterministic in nature. So if you look into this SR point-to-multipoint policy, the essential things are what is the root node and what are the set of leaf nodes. If we have this information, then we can compute the relevant path. So in some of the use cases, these two details, like the root node and the set of leaf nodes, are very deterministic in nature. Like, for example, we have a video camera which basically sends the video feeds to a set of servers for different types of processing, like ad splicing, or even enhancing the resolution, or even to create different types of resolutions before sending it to the CDN network. So here, the video feed is going to be fixed, and so whatever the node that is connected to the camera, that's going to act as the root node. And those set of servers who are receiving the traffic, the video feed from the camera, they are again fixed. So the devices which are connected to the servers, they are the leaf nodes. They're going to act as the leaf nodes. So it's pretty deterministic in nature. In this case, all we need to use is the static tree, where we can leverage the controller to compute the path and instantiate those state entries in the relevant devices. On the other hand, there are other use cases where the receivers may join or leave the tree. In which case, the static tree may not be helpful, because we can't go and make those changes every time manually, or even instructing the server to do it. In such cases, we'll be using the dynamic tree-based point-to-multipoint policy. The point-to-multipoint policy comprises of multiple replication segments. So within the replication segment, if you look into those segments, it basically receives the traffic, replicate it, and forward it to different downstream nodes. How do we do this? We are introducing a new type of segment ID called replication segment ID or tree segment ID. So if you remember, when we discussed about the architecture, the basics of segment routing architecture, we discussed about how we can define our own segment ID with its own associated semantic, either to strictly forward it to a specific link or to follow the shortest path. So this tree segment ID or the replication segment ID have a forwarding semantic of replicating the packet and sending it to different downstream nodes. So the list of downstream nodes can be programmed by the controller. By stitching all those segments, the replication segments together, from the root node to the set of leaf nodes, we'll be able to build the end-to-end point-to-multipoint tree. Let's see what is the functionality of path computation element or the controller. We saw that it plays a key role to help us build the point-to-multipoint tree. And we also saw that this solution, the SRP2MP policy, is a controller-based approach. So the functionality, the PCE functionality comprises of 4 steps. The first step is obvious, to learn the topology. It's not much different for unicast or multicast. The next one is to learn the tree details. The tree details, what is the root node? What are the set of leaf nodes? And what is the candidate path information, like what type of traffic or services required for this particular traffic? Once we have the topology details and the tree details, the third step is to compute the path and instantiate the relevant state entries on the relevant devices. We'll look into each of these steps. So learning the topology, like I said, we'll be using the BGP link state protocol or the address family, which basically have the ability to extract the entire details, the link state topology information from the underlying IGP, irrespective of the protocol. So using this, the SR PCE will have the entire link state information. Now, the one thing that we would like to highlight here is it also have the ability to get the SR native algorithm specific details. Like for example, if you have multiple planes, FlexAlgo specific information, or the links are configured with different colors, SRPCE will have the ability to have all those information. So when I say holistic information, it have all the details about the topology. So this way, we'll be able to compute the relevant path based on different link affinity or even other constraints. Learning the tree. So for point-to-multipoint policy, the essential thing is to learn the tree details, which is the root node and the set of leaf nodes. For any point-to-multipoint tree, either this can be statically defined. In case of deterministic use cases, we can precisely say, this is my root node, and these are the set of leaf nodes. And in case of dynamic tree, we leverage the dynamic protocol, the BGP, MVP, and auto-discovery protocol, which basically is used to exchange all those leaf information and the multicast, the C multicast, the customer's multicast flow details between the edge devices and the MVPN. So in case of static, it's up to the operators to define it in our SRPCE. And in case of dynamic, it can use the BGP protocol, the relevant BGP protocol extensions. Once we have the tree details, we already have the entire topology information. So the third step is to compute the path. While computing the path, we can either instruct the PCE to just follow the default behavior to compute the path, or even feed in the relevant constraints, like should it be a shortest path, should it be a disjointed tree, or any of those constraints can be fed to the SRPCE, which will use those relevant link affinity and other details to compute the path that basically satisfies the candidate path requirement. And finally, it uses the PISA protocol, the PCE protocol extension, to create the state entries on each of the devices. So if you look into the state entries, you can see that the replication list, even though the other details like the tree ID or the tree set will be nearly the same, the replication list will vary depending on the devices, because the transit devices may have to replicate to different downstream devices. For example, node A will be sending 1 copy to node B. On the other hand, node B will be sending 2 copies, one to node C and another one to node E. So all these state entries will be instantiated on the relevant devices by the SRPCE. So this is our entry point where we just go and instruct what type of tree, how many trees are required, what type of tree, and what is my candidate path information, what is the root and the set of leaf nodes, and the SRPC will take care of the rest. It computes the paths and it instantiates those state entries in all the relevant devices. So the tree SID, or the P2MP tree, is now instantiated right from the root node to the leaf node. The next step is to map the multicast traffic to this tree. What am I going to use this tree for? How many multicast traffic are required to be steered over this point-to-multipoint policy? So this state informations are required primarily on the root node. On the root node, we can define the multicast traffic, the SGs, the source and the group information, which basically will instruct the root node to use this particular point-to-multipoint tree as the egress interface. So the outgoing interface list will have this point-to-multipoint policy, and we may have one or more multicast traffic that will be mapped to this particular point-to-multipoint tree. On the leaf nodes, the action is to use this incoming interface. Incoming interface list is your point-to-multipoint policy, so the action is to decapsulate and then perform a lookup in the relevant multicast table to forward the traffic out. This is the example configuration on the SRPCE for a static tree. So if you remember, I mentioned about the essential things that are required for configuring SR P2MP policy, which is define the root node and the set of leaf nodes and your candidate path information, what type of path is required for this tree. If you look into this configuration, first it says, it's the PCE address configuration. And here you define all those list of leaf nodes. And then we create the policy, set the root node, and associate the set of leaf nodes here, the candidate path information. Should I include a specific link or exclude a specific link affinity and so on. With this configuration, the SRPCE will compute the path. It will identify the optimal branching points between the root node and the leaf nodes in a way that basically satisfies all the relevant candidate path constraints. With the Crosswork 5.0, the configuration the tree configuration can also be performed from the Crosswork UI. So under traffic engineering, the tree SID, we can create this. And again, if you look into those essential details that needs to be filled, it would be the root node, the set of leaf nodes, and the candidate path information, the constraints, and other details. Okay, so with this, the path computation element will be able to build the point-to-multipoint tree and instantiate those state entries on the relevant device. Now, the next step is to create the relevant configuration to map the multicast traffic to this, the point-to-multipoint tree. And if you remember, it needs to be done on the root node. So this is a sample root node configuration, where you can see, you have this point-to-multipoint tree, which basically will identify the P2MP policy, and you have the set of, the SGs statically defined. So it either could be on the default multicast table or even on the VRF tables. And on the leaf node, the action is to decapsulate and then perform a lookup in its table. So it's not required to perform any mapping. Rather, we need to define what are the set of policies that this particular leaf node should be part of. So here in this example configuration, you can see that we say the static way of defining all those policies to which this particular node should be act as a leaf node. With all these configurations, let's quickly look into some of the state entries that will be created. So we saw that we'll be creating the relevant configuration on the SRPCE, which is responsible for computing the path and instantiating the state entries. And then on the root node, we'll have the relevant state entries, which basically maps those multicast traffic to the SR P2MP policy. And on the leaf node, we will be having the decapsulation action. So on the SRPCE, this command, the show PCE LSP P2MP, will list all the SR P2MP policies. And within each of those policy, we can have all the other details, like what would be the root node, the set of transit nodes, the leaf nodes, and the candidate path information, the tree SID that's been used. All this information will be available here. So by logging into this SRPC, we'll have a holistic view of all the P2MP policy that we have configured and instantiated in this network. The next command is on the root node, which is node A, where you can see it's been associated with different S, G, where we are using this particular P2MP policy as the outgoing interface and have the label, the relevant label. So this is the replication segment ID or the trace that will be used by the node while forwarding the traffic. And the leaf node will have the same value, which is 18001, to decapsulate and forward it out. So basically, it will perform a lookup in the multicast table. The transit devices, in this case, node B, will have the replication action where the incoming one is 18001. So when it receives a packet of 18001, the action is to replicate the packet and send it to two different interfaces towards node C and node E. So this is a pictorial representation of how the forwarding works. As you could see here on node A, we'll have two tables. So when we receive the multicast traffic on the root node, it performs a lookup on the first table, which basically says, it needs to be encapsulated with 18001. So once it performs this encapsulation, the next lookup is performed in the segment ID table, where for 18001, the action is to swap with 18001 and forward it to node B. So the traffic will be forwarded to node B. Now, node B receives the packet as a SR encapsulated packet, and the topmost segment ID is 18001. The action here is to replicate the packet and send it to node C and node E with the same segment ID, 18001. On the node C and node E, which are acting as the leaf node, the action is to decapsulate. So the SR header or the label will be decapsulated and then perform a lookup in the multicast table, and the traffic will be forwarded out. Let's quickly discuss about one of the interesting use case, which is the disjointed tree for high resiliency. Over a period of time, the one ask from different customers is like, can we have high resiliency for multicast traffic, trading floor, or any of those applications that basically uses multicast. So we do have this for unicast for the past 6-7 years, or even more than that. But for multicast, we had some solutions like MOFRR, but again, it's not constraint aware. So using this architecture, by leveraging segment routing architecture and this introduction of SR P2MP policy, we can achieve this. How? If you remember, we discussed about SRPCE, which is capable of having a holistic view, not just the default, but even multiplanar solution with link affinity and other details. But using this, we can build the network in a way that we have two different planes, the blue plane and the green plane, which will be populated in the SRPCE's link state topology. By sending a request for P2MP policy, which basically does not overlap with any of these planes, like building disjointed tree, where the blue one will be requested to not use green, and the green one will be requested to not use blue. So using this, we build two point-to-multipoint tree with its own tree set that originates from root node and terminates on a set of leaf nodes with its own tree set. So it's up to the receivers to either receive the traffic from the green plane or the blue plane. So this way, we can achieve this high resiliency for multicast traffic using totally disjointed network. So this is not just the only use case. There are other use cases like we can even build a tree based on other constraints like low latency. Point-to-multipoint, make before break. So we saw that we can build a latency-aware point-to-multipoint policy. Now, it always comes with a requirement that it needs to be optimized so that we can assure that whatever the constraint is actually maintained. So how do we do that? It basically uses the make before break concept. So let's assume that there's an event happening. We have a network which either the event could be like a new link coming up, which gives us a better path comparing to what we already have. Or even it could be like a violation. We saw that we had a link which was satisfying the threshold, the latency or other threshold, and now it's been violated based on the performance measurements. So there is an event, some event that happens in the network, which will be notified to the SRPCE based on the topology change, a new link up, or even the violation of the IGP or the TE metric. Once the topology change is notified, the SRPCE will recompute the path to identify which other path is actually satisfying this particular constraint. And once it compute the path, it updates the transit devices and the leaf nodes. Again, not the root node, but the transit devices and the leaf nodes first, leaving the old entries as stale, so that the other entries will be used. So while all these update is actually happening, the root node is not yet aware, so the traffic will be steered over the old path. Once the state entries are created on the transit devices, the next step is to update the root about the new tree. And once the root node confirms the update, sends a confirmation to the PCE server, the PCE will remove the other details, the old details from the table. So as you could see, we make before breaking. So this way, we nearly can offer the service in a seamless manner without any interruptions. So we saw that there are other use cases which are dynamic in nature. Pretty simple example is the multicast VPN, where based on the interest to receive a traffic that we receive from different customers, we may have to build different type of trees, the data MDT, for example, in the MVPN. So in such cases, how can we use SRP2MP policy? I mentioned that for dynamic, we basically will be leveraging the dynamic protocol, the BGP MVPN auto discovery. So whenever we have this configuration, let's assume that on the PE devices, PE1, PE2, and PE3, we have the relevant configuration, which basically is enabling multicast for a specific VPN. Once we have this, the PCE server will send a request to the SRPCE asking to create a point-to-multipoint tree. While doing so, it will include the relevant details like the MDT tree that is assigned for this particular MVPN or the VRF customer. When the SRPCE receives this information, the inbound request could be considered as the node. The requesting node is considered as the root node. So if you remember, for SRP2MP policy, we need three essential things. The first thing is the root node. The next thing is the set of leaf nodes. And the third thing is the candidate path information. So the node that is sending the request will be considered by the SRPCE as the root node. Now, to receive the set of leaf nodes, the PCE node, the PE node, will use this BGP auto discovery to identify the remote nodes which are also participating in the multicast VPN for this particular VRF. So here in this case, using a combination of these RT value, PE1 will be able to identify that PE2 and PE3 are also participating in this multicast. So it sends a request, update leaf node, to SRPCE saying, I'm the root node. Now, these are the set of leaf nodes that should be part of this particular point-to-multipoint tree. And along with this, we can also have this candidate path information that could be configured on PCE. So using this, the PCE server now knows this PE1 as the root node and the set of leaf nodes and the candidate path information. It computes the path and will create the relevant state entries on the transit devices. And on the root node, it will be associated to map all those traffic from the VRF. And the PE2 and PE3 will be using the inbound or the incoming interface list as the point-to-multipoint policy, and use that to identify what would be the multicast table, the respective VRF's multicast table, to perform a lookup. So with that, I'll invite Mankamana to talk about the distributed approach. Over to you.
Good morning, guys, and thank you. It looks like there is some issue with slide deck. It looks like the latest changes slides were not there, but it's fine. So we are going to talk about MLDP and MLDP-based point-to-multipoint trees in segment routing. And mostly today's session is based on kind of a troubleshooting, that what exactly you will look into router, how will you confirm whether things are working. And we will talk about two of the choices. One is the global table MLDP, which is end-to-end MLDP. And the second option we will talk about is MVPN-based. So when we are talking about segment routing and we are going to use MLDP, so in that case, we need to enable LDP only for multicast. So when we enable LDP only for multicast, what is the impact you are going to see? So if we see in this routers. Right now, I have LDP without MLDP only capabilities. So in this case, for IPv4 prefixes, we have all the routes and bindings being advertised across the network. As soon as we go ahead with config, where we say that we are going to use LDP only for MLDP, we will see that there are not a single binding there is not any unicast routes being advertised here to the next of the routers. For MLDP, if we are using in segment routing, we will be enabling this particular capabilities. How exactly label mapping works? So we have a network here with 2P and which are acting as a receivers, and we have a source. These receiver P, they are going to build hop by hop tree. When they are building hop by hop tree, they are going to do some kind of message exchange. MLDP message is being exchanged using LDP as a transport mechanism here. And the amount of information which we are going to carry, or the important information which we will be carrying, is the FAQ element. So here there are 4 important elements. The first 3 elements are going to define any tree uniquely. So here we have a type. So type says that what type of tree we are trying to build. In this case, we are building point to multipoint. Then who is root, where the source is sitting. And third element is the opaque value. This particular value is going to map your flow or group of flows or your services, any flow within VPN. So this will be identified by the opaque value. And then the last one is we have a label here. So label is nothing but the local label which I'm trying to exchange between these 2 nodes. So in this case, if the topmost left P is exchanging this particular FAQ with P, it is going to send which label I'm going to use. The replication here, when we are using MLDP, there are 2 parts. In the control plane, in the core router, we are using modified LDP. So when we say modified LDP, we are not exchanging any of the unicast route using LDP. The only MLDP TLVs are being exchanged with LDP. And the second part is, in case of, in the data plane, we will have point to multipoint replication entries created. So if at any node, if I look at my replication entry, it will look something like I have incoming labels and what all are the outgoing labels with outgoing list. With MLDP, we have FRR protection as well, and we have both LFA and TI-LFA. So in this case, when you have MLDP session running between P and P, if the top layer of the network, each of these links can be protected via LFA or TI-LFA. So in this case, backup label will be pre-provisioned and pre-programmed in case of any failure. With respect to the signaling within a box, so if I look at this particular node here, which is P router, so in the P router, I have received a binding from the top left and the bottom one. And these two routers, they have given what is the label they are expecting. I hope this is readable towards end. It is pretty small font. So they have exchanged their label, which is the label they are expecting traffic on. And I have my own local label. So this is what MPLS binding will show at any of the node. These bindings will get converted to my tree database. So this tree database says that I'm building a tree which is of type point to multipoint. My root is 10.0.0.2, which will be this node. And now here at P, when I look, my upstream neighbor is the P, which is the root node. And I have 2 downstream neighbors where I have received label binding from. And the remote label, this particular remote label is nothing but what P has exchanged that I'm expecting traffic for this particular given tree over this label, which is 24004, and the other PE has provided another local label of their own, which is remote for this P node. When you convert, or when you look at the LFIB entry or forwarding entry here, the forwarding entry will look like that I have local label where I will be receiving traffic, and I am going to replicate it to two different labels to two different outgoing interface. Before we jump into the lab, or I would say step-by-step procedures for MVPN and base MLDP, let's little bit get to know about MVPN. So MVPN is nothing but my multicast services over VPN. And when we are trying to build multicast services over VPN, there are different types of tree which we create in service provider network. One of the tree is default tree. So default tree is a kind of a virtual LAN segment which you are creating across the network, where any of the PE, when receives a traffic on given VPN, these traffic will be sent to all of the rest of other PEs in the network. We have provision for data MDT. So data MDT is for the cases where you really don't want all the flows to be always delivered to all the locations. There are many cases where you have heavy video traffic, which you want it to be delivered only at certain specific sites. In that case, you can move those flows to specific MDTs. And the third one is partition MDT, which is the most popular one. And one of the reasons why this is most popular, because this gives you a capability where you can have a case where you build your MDT only based on need. So it is a subset of a default MDT. In case of default MDT, as soon as we provision our multicast routing and VPNs, this whole full point-to-multipoint mesh of tree will be created. On the other hand, there may be a case where you have co-located source host, whereas there are large amount of sites where only receivers are sitting, and you really don't want to create full mesh of trees. In that case, partition MDT is the one which gets useful. So just to see that how exactly signaling works in MVPN part, we have two parts here. So per VPN, we are going to create underlay tree which defines that how exactly all of PE devices which are hosting the VPN are going to get connected, or how exactly core tree will be built. And once we have built the core tree, the overall VPN plane, this tells about that I have a core tree within PEs, and then how exactly I'm going to do my signaling for customer multicast flow. So we have few choices here. One is BGP and another one is PIM. Today we will be looking at BGP, that how exactly route exchange happens, what field we look into, and how will we identify whether these signalings are going fine. With respect to data plane, that we have multiple encapsulation options here when we are sending traffic over the core trees. One of the options which we are going to talk about is MPLS label stack today for profile 14. We have we are confused that why we have so many profiles. So I would like to just touch on this area, that this is regular service provider network where you have service provider cloud. There are multiple sites where you are providing services to your customers. These customers wants to do end-to-end multicast. How exactly end-to-end multicast is going to happen? So there are three segments here. One is one segment of multicast is happening in customer network, where finally they are coming and getting connected to the service provider network. Then we need to do something within service provider network. Then we have another multicast protocol running here between PE and CE. So let's see, the first thing is, what are the encapsulation choices we have? So we need some way that I should be able to encapsulate any customer packet within service provider network. The reason why you need encapsulation here, as a service provider, you may be providing service to multiple customers. So if you have multiple customers, you want to make sure that one of customer or one of packet from customer A is really not going to map with customer B packet. So you need some kind of encapsulation to provide a secure transaction between PE to PE devices. Then the second part comes, how exactly these PEs are going to find each other with respect to multicast services. When you have provisioned these services, how exactly we are going to identify that which all sites these services have been provisioned. And a third thing is that which method I'm going to create provider tree here. These are the three important aspects. Then we have some of other aspect as what is the P to C multicast protocol running. Then we have what P to C routing is being used. And the last important part is how exactly we are doing the binding of IP multicast to my service provider network. If you look at the choices, the classical support, we have IP, GRE, PIM, and bunch of other protocols. With the next gen, we have all of these list of protocols. These are the three parameters with multiple combinations goes and makes different profiles. So when we say profile 0, we talk about GRE with PIM signaling. When we talk about profile 14, we say that BGP-based signaling with partition MDT. So when you pick one of the choices from these long list, you will be able to create one of the profiles. So these 30 profiles are nothing but predetermined, pre-tested, different combinations of these segments. So we will talk about two of the profile. One is global MLDP in-band signaling, and the second one is profile 14, which is your partition MDT. These are the two profiles which are most commonly used in MLDP. So if we look at global in-band signaling, the very first thing is you want to check how the config is. So the config here, the multicast routing is getting enabled at both of the PE devices. The important line here is MDT, MLDP in-band signaling. So what I'm talking about, that this configuration says that I'm operating at the global table and I'm enabling in-band signaling for IPv4. The same config is going to be present at the other PE as well. And if I look at and apart from that, I will have LDP configured with MLDP only option. And in that case, I'll be able to see all the neighbors here. So PE2 is seeing P as a neighbor, P has two neighbors, and PE1 has one neighbor here. The second part is once we have configured MLDP only SAC, what exactly you will be able to see. So as a MLDP summary, you will see that not any unicast routes or any unicast prefixes are being advertised here. And with respect to capabilities, my point to multi-point capabilities are turned on. So many times when you are debugging MLDP network or your deployment, if it has some issue, these are the initial step to take a look in case there is some config mismatch where maybe MLDP itself is not enabled. So once we make sure that all the basic configs are done, then we can go to the next step, which is checking the neighborship, whether MLDP neighborship has been up or not. So when you have configured MLDP, they have exchanged their capabilities to doing MLDP signaling. And after doing the initial exchange, we would have built our MLDP neighborship. Then the next step comes is we sending a join. In this particular router, I have created a static join so that I can simulate the overall binding or setup steps which is happening. So I configured a static join here at PE2. My source is 11.11.11.2, and group is 232.1.1.1. For multicast, when you have any join coming, the very first step is I need to check how exactly I'll reach this source. So having reachability to source in unicast is important before I can start building multicast binding. So I'm going to, the first step which will happen here is check how exactly how to reach 11.11.11.2. And I identify that my next hop is via BGP. So I need to take a look whether I have route for this particular next hop, which is 11.11, 11.2 in my rib or routing table. So rib is pointing that yes, it has been learned, and it has learned via this particular BGP next hop. And if I want to reach BGP next hop, what is my underlay reachability? So we need to check two reachability. One is I have overlay reachability to the BGP next hop. And the second thing is I have underlay reachability, whether I can really build hop by hop tree. So these are the steps to check when you have your join coming on the last hop router. Once I have received my, once it is clear that there is a reachability for source, the label binding will start. So label binding will start from PE2. So PE2 says that I am building a IP. So this particular OPEC value, in case of in-band signaling, we map each flow as one OPEC value. So I'm building IPv4 with source and group address rooted at 192.168.0.2, which is the PE address or the BGP address for a given source. This particular label will be sent to the next hop, which is P router. Here I'm saying that downstream is local interface. So my egress interface is the local interface here, and incoming interface is going to be the next hop, which is 1.0 here. This particular label will be mapped here. Here you will see there are two entries for the same OPEC value. One is that my upstream is PE2 and my downstream is going towards PE1. And the PE1 entry shows that I'll be exchange or label exchange from the PE1 towards PE side, whereas this traffic is going to come locally here. So with respect to your multicast state here, the previous slide showed the MLDP states where we have done the label exchange from PE to PE via P router, but only both of the P's, they will have entry of your multicast state. So P router doesn't have any multicast state. In the P router, if I look at my mrib entry, and my mrib shows that incoming is going to be the LMDT interface. When we say LMDT, it is nothing but my MDT interface from the core, and outgoing interface is the local interface where I had received join. Same thing on the PE1, you will be able to see mrib entry says that my outgoing is LMDT and incoming is the local interface where my source is sending the traffic. So we will be able to, first thing we'll be able to confirm if join really went hop by hop by looking at our MLDP or MLDP exchange. Then the second important aspect to check is what is the multicast state in ingress and egress. These are the only two places where we will have multicast entry. And then how exactly that data plane is going to work. In this case, we have our forwarding entry here at P1, which says that I need to send traffic on label 24002. So I receive a IP multicast traffic. Since P1 is the first hop router for MLDP network, I am going to have encapsulated it with label, and this label traffic will reach to P. P has an entry that if any traffic which comes from 02, I need to swap the label and send it to PE2. So it is P does the label switching. At the PE devices, we do encap and decap. So when it comes to debugging the global table MLDP, we have 3 or 4 steps. First step is just to check if MLDP bindings are up, if MLDP neighborship is up. The second step is on the last hop router, when I receive join, do I have reachability to source? And if I have reachability to source, who are my next hops? Then the third step is the last hop router starting MLDP binding hop by hop towards source. So when we are debugging, we need to go hop by hop, starting from last hop router, looking at the MLDP database and what is the label exchange we have done, and we can go all the way till root. And the last step will be to looking at the actual forwarding. If my forwarding table is populated well and if it is taking place. So before we go into BGP-based signaling, if there is any question. When we are doing MVPN, so BGP has found a new role. And the role of BGP is doing two signaling. One is your auto discovery, and second is customer multicast signaling. So as we were talking about, when we are talking about MVPN, it had two parts. The first was how exactly each of these nodes are going to identify each other, or how they are going to discover each other. So that is going to be done via BGP. And the second part is when you have customer multicast signaling, or when your customer is sending joins, how exactly we are going to take it or in the overlay from the service provider network. So that is where BGP will be used. So BGP has a new address family for next generation MVPN, which is IPv4 MVPN. And then we have multiple tunnel attributes defined. These tunnel attributes say that what exactly underlay tree mechanism we are going to use to build in core tree. And then we have NLRI. These NLRI are consisting of source, group, and bunch of BGP predefined addresses. For example, originator, and then route distinguisher. So in this case, if we look at MVPN profile 14, we are looking at P2C protocol is mostly PIM or IGMP, which is your customer network. We will be using BGP here as an overlay for auto discovery as well as to carry multicast signaling. And then again, your customer network has PIM and BGP, PIM and IGMP. Partition MDT, once just to refresh it, partition MDT is multicast distribution tree, which will be built only on demand when you have at least one receiver. So when you configure your MVPN or BGP auto discovery for profile 14, initially we won't build any trees. So we will be able to discover each of the nodes, and these nodes will be discovered, entries will be kept, but there is no multicast tree being created. As and when your at least first receiver comes, that is when you are going to request to build a tree towards root. So these trees are kind of subset of your default MDT, which we were building completely full mesh. And this is more useful because in real scenario or all the deployment scenarios, source and receivers are really not fully distributed across the network. So most of the cases, sources are sitting in some co-located areas or certain areas, whereas you have receivers at multiple locations. So we will go step by step on how exactly this MLDP profile 14 looks like. So when it comes to config, we have two things configured here. Under multicast routing, we are going to go into VRF, and under VRF, we have configured that we want to do partitioned MLDP point-to-multipoint. At the same time, you will see there is something I have configured here, data MDT 10. I'm going to talk about what exactly this data MDT 10 is in following slides. So for now, we will just focus on partition MDT. So we are saying that as a multicast routing in this particular VRF, I am participating and I want to participate in partition MDT. On the LDP side, I have turned on capabilities, which is SAC MLDP only, and this config is going to be present in both of the PE devices. If I look at P device doesn't have any of the PIM config. There is no multicast routing config here present in PIM, which is related to this given VPN. I have only LDP, which is turned on the P router. With respect to BGP, we have to turn on this next gen MVPN capability, which is address family IPv4 MVPN. Now with these two config, in the PE devices, we have done two config. One under VPN, I have turned on partition MDT for multicast config. The second thing, in the BGP, I have done MVPN address family, I have turned on MVPN address family. Just by this config, what exactly is going to happen? So first thing is, I will be seeing that I have MVPN neighborship in the BGP. So PE2 can see PE1 as a neighbor. If we had multiple such PE devices, I should be able to see in the BGP MVPN summary that I have all of these neighbors which are up. So when you have deployed or when you are debugging your MVPN network, if there is a site which is not receiving traffic or it is not able to communicate, the very first thing is to take a look if there is really auto discovery done or not, whether we have been able to see that particular site in the BGP MVPN summary or not. Then the second step is auto discovery. How exactly the entry in this table happened? This entry in this table is happening using these routes, which is auto discovery route. So each of these router, they have to send their they have to announce themselves that I am participating in this particular VRF for multicast routing. So if I see MVPN route type 1, I will be seeing two entries here in my case, because one is the one which I have originated myself, the other one is what I have received from the neighbor. So this is the second step to take a look whether auto discovery routes have been exchanged or not. At this point of time, we have only exchanged auto discovery routes. There is no tree built yet. We have not built any tree between these two sites. This particular route, which is route type 3, it is very important route for partition MDT. You will see there is a star entry here. So there are two star entry. When I say star, source and group both are all zeros. So these zeros are nothing but I am saying that I am participating in any multicast, which is I can have any source or any receivers. So these star entry in route type 3 is signal to the other peer that I am participating in partition MDT. You build tree towards me only when there is a need, only when you have a receiver. But if we go little deep into this particular route, what it carries? So it carries very important information. We were talking about in MLDP, when you do signaling hop by hop, we need to carry some FEC. And that FEC carries the root information and it carries some opaque value which can determine a given tree. How exactly P2 is going to get that information? And this information is coming on route type 3, which is advertised by P in the left hand side, P1 here. So if you look at P1 advertised route in detail, you will see something as ID here. This ID carries all these information. So I have highlighted the colors that how to decode this particular ID. So the first part of this ID tells that what is the FEC type. And value 6 is for point to multipoint. Then it talks about what is the AF type. And after that, it gives length. What is the length? And this particular part gives me the root address. That if you want to send any label mapping, who will be the root? This is very important because whatever root address here we are advertising, we must have IGP reachability or underlay reachability here. It is really needed because it may happen that you might have overlay reachability, but your underlay doesn't know how to reach this particular address. So we have to make sure that root address is something which has underlay reachability. Then we have opaque type, which says that I am sending with global ID and what is the length, and global ID is 1. So this 1 is nothing but a tree ID for this particular tree. What this whole message means that if P2 wants to build a tree towards P1, it has to use these label mapping, these opaque values to exchange the label mapping. At this point of time, we don't have any joins. We don't have any tree being created. If you look at your MLDP database, both place, there is only one global ID created, which is for itself, rooted at itself. So I say that my global ID is 1, my root is, I myself is a root. And same thing at PE1, that I myself is a root. At this point of time, nobody has joined anyone. But both of the sites, they are ready to join any tree or host any tree as a root. Then if we send a first join, what will happen? So when we send a first join, same rule applies what was there for MLDP in-band. That the very first step is, I need to see if I have reachability to this particular source, which is 11, 5, 120, and 20. So you need to check if you really have reachability to your source for which join has come. So I need to take a look at reachability in VRF table, and after that, once I have reachability in the VRF table, I need to see if this BGP next hop I can reach from the underlay, because my tree, when I am building hop by hop trees, these trees are going to be built in the underlay. So I have to have underlay reachability as well. So this is the very first step to take a look when you are receiving a join, but these joins are not taking any effect. So in that case, the first thing I would check is the reachability, unicast reachability. Second part is, as we were saying, that when you have partitioned MDT, when you receive join, that is the time you will start building your underlay tree. How exactly we are going to build underlay tree? So first thing is, I verified my unicast route to a given source. Once it has passed, second step is, I want to verify whoever is my next hop, whether that next hop is capable of doing partition MDT or not. And if it is capable of doing partition MDT, what is the FEC I have to use? So it is going to verify for this particular next hop, do I have any star entry in BGP? And if I have star entry in BGP, what is the FEC value I have got? What is the TLV or OPEC value I have received, or what is the ID I have received for tree? What exactly I need to join? So I do two check here. First check is source reachability. Once I have source reachability, I identify who is my BGP next hop. And once I have BGP next hop reachability, I look into my BGP table whether I have a star entry. Once I identify star entry, I get that particular FEC value and start building underlay tree. So I start building the underlay tree with global ID is 1 and my root is 192.168.0.2. This was my BGP next hop, which is nothing but PE1 IP. And then my local label. What is the label I am expecting traffic on to receive this particular traffic? This mapping reaches to P. When P receives this mapping, P has to make its own entry and it has to do the label mapping with P, which is its own next hop. So here we will be able to see two entries. One is my upstream neighbor and another one is my downstream neighbor. That who has sent me the join and where I am sending my join to. So these entries will show you whether your underlay tree is being set up or not for any given PE. So remember, at this point of time, even though I have received join, I have only built my core tree within service provider network. There is no information about which flow is getting mapped into this particular tree. So at present, I received a join, I verified my source reachability, I verified if that particular next hop PE or ingress PE is capable of doing MLDP partitioned MDT, and I have sent my underlay tree to join core tree. So the next step which we are going to look at it is what is the multicast state in the last hop router where I had received join. So if you check your MRIB will show that my incoming interface is coming from tunnel, which is core facing tunnel. my outgoing interface are my local interfaces, and same thing will be seen in PIM entry as well, that my outgoing interface or forwarding interface is local interface, incoming interface is the RPF interface. We keep track of RPF interfaces as well in the PIM database. So you will have to make sure that these entries are populated in last hop router before we can really go and start debugging further steps. We have, so till now we had received join, we had created our underlay tree, but now the time is that somehow I should be able to map these particular customer IP flow back to tree, and that is where this route type 7 comes into the picture. The last hop router does two things. One is building the underlay tree, which we already built. Now PE2 has to notify PE1 that I am interested in this particular source and group, and that is where new BGP routes will be exchanged, where it will carry SG information and it will carry where exactly this SG is coming from, which is the next hop. So these routes will be sent from PE2 to PE1. In the PE1, when you look at your route type 7 entry, you should be able to see that who is the next hop who is sending these particular joins. Once we have received the overlay join, that is where multicast will now create these mappings. So if you look at multicast table here in the PE1, it will show that now I have received a join and I need to send this traffic over this particular tunnel, which is LMDT tunnel, which is my label-based MDT tunnel and towards core. From the last step, once multicast has created its state, I would have created my point-to-multipoint forwarding table where I'm going to receive IP multicast traffic, encapsulate it, and send it as a label traffic, and these label traffic will go hop by hop all the way till your last hop router. So once it reaches to last hop router, here we will remove the label and we will forward it to the local interface. So till this step, we had only one join. We received one join, I created one underlay tree, that's all. What will happen if I receive another join in the same VRF? Do I need to build another tree? And answer is no. Because if you receive another join, the only thing what you need is to be able to signal your ingress PE, which is PE1, saying that I am interested in one more flow. But your underlay tree has been already built. There is no need to really create one more underlay tree. So if I look at my config and show commands here, I have two SG joined, but my MLDP database, so MRIP shows that I have two entries, but if I look at my label database or label database binding, I have just one entry. And the reason why I have one entry is because I have already created my tree, which is aggregated tree. The second flow will also be mapped into the same tree. So before we go to, yes. Yes. So the signal which we were sending to source, it is route type 7 about this particular SG. So your underlay tunnel is set up, but you may, as an ingress P, you may be getting 100 flows, but you are not going to map all the 100 flows to the tunnel unless there is at least one active receivers. So that is where when you receive a new join, you have to notify to the source.
So the source here is not actually the ultimate source of the multicast traffic, rather the ingress device, the ingress PE.
Yeah. Sure. But there is one catch here. If we had multiple devices, let's consider I had P3 here, and P3 also did exact same config or is interested in exact same traffic. When I do overlay signal, my route reflector may not send it to ingress PE all the time. It will merge it. And the reason it is going to merge, as long as there is at least one active receiver which is known by ingress PE, it will keep sending traffic on the tunnel. When you join underlay tunnel, you will receive all the traffic anyway. So you don't really need to populate all the BGP message to ingress PE. So route reflector is going to suppress it, unless you really configure explicit configuration which says that you have to kind of do add path where you keep signaling everything. So next, yeah. Any question? Oh, yeah. So next part is data MDT. So till now, what we saw is all the flows are being mapped to single tree. But we had a config something called as a data MDT. Data MDT gives you flexibility where as a service provider, per VPN, you may want to have 10 trees created. And you want to have a flexibility where some of the flows you want to send over one MDT, some of the flows you want to send over other MDT. So for that, we can create data MDT. When you configure data MDT, there are two ways to switch any flow into data MDT. One is threshold. This is nothing but which you say that if my bandwidth of a flow is going above and beyond X PPS, I want to make sure that I build a new tree. I don't want to send it to everyone. Our second one is immediate switch. When you say immediate switch, what it means that as soon as I receive a join, I'm going to move to new MDT immediately. These data MDTs are nothing but you are creating 10 different trees here. If I have configured MDT data 10 immediate switch, so what I'm going to do, I'm going to create 10 trees. But what will happen with 11th flow if I have 20 flows? So by default, we go round robin. So first request for first flow goes to tree 1. Second flow goes to tree 2. Third flows go to tree 3. It will go on till 10th, where 10th flow goes to tree 10. When I get 11th flow, I will go back to tree 1. So this is the default option. There are multiple other ways where you can explicitly create a policy that these 4 flows has to go only in one tree. But by default, we do round robin. So we enable data MDT something like this. So let's see what will happen when I create data MDT. So as soon as I create data MDT and I send a to join. So I had picked option saying that I want to switch to data MDT immediately. So you will suddenly in BGP see more SG route type 3. So earlier, the way I was identifying how to join underlay tree was using star entry. Now with data MDT, I will get SG entry as well as route type 3 that is going to carry this particular ID, the ID which we had decoded. So these IDs are nothing but the underlay tree IDs, that how exactly you will be joining the underlay tree. If you want to verify this mapping can be verified using SOAP-M MDT cache, where we map that this particular customer flow is mapped to which global data, global ID. Now if you look at your tree building, I have created 2 trees here. One is global ID 4, one with global ID 6. So end to end, I would have created 2 trees for 2 flows because I had 2 joins, and each join is now creating its own tree. If you want to try out this profile 14 in lab, we have walk-in lab. All the steps which we did, you will be able to verify each of them, and it takes around 45 minutes to really do end-to-end profile 14 trial. We have it in walking lab here. Thank you, and that's all.